We'll start today. The goal for today's lecture is to talk about three important results in general state Markov Lipschitz processes. The first result, which is the existence of optimal solution and the existence of V star. So that's what we'll be doing first. We'll prove the result based on the assumptions we made in the previous lecture. And then we'll talk about Lipschitz continuous value function and monotone value functions. So those are the three topics. I'm assuming we'll be able to finish the monotone part, but if we are not able to finish today, I'll finish it in the next lecture. Tuesday is a holiday, so we'll be meeting next week on Thursday. Okay. So what was the setting? So I have my state space S. I had mentioned it's a subset of Rn1 cross Nn2 cross Zn3. Both the state as well as the action space are subsets of this. And you can pick, like you could have a real component, you could have natural numbers, you could have integers. The results, the ones that I'm going to be talking about today are in extremely general spaces, but because I don't expect you to have taken real analysis, we won't talk about the extensions to general state spaces and general action spaces. We had the cost function from the graph of A to 0 infinity is inf compact. So that was the first part, second part. And the third part, which was that the transition kernel is weakly continuous. So in order to make the proof easier, I'm going to assume that the st plus 1 is given by capital F of st atwt. Wt is IID, and the distribution of Wt is n of w dw. Now, of course, this implicitly assumes that you have a real number, real valued or Euclidean valued noise. But again, because I want to make sure that in the lecture everyone understands everything, I'm making the simplifying assumption, but the result holds for very general noise processes. Okay. I will need two other results today to be able to prove the main theorem. The first one is Fatou's lemma. So you have a sequence of function fn from a arbitrary set x, measurable set x to r. Fn is greater than equal to 0. So it's actually non-negative, so maybe I should write 0 to infinity instead of r. Then integral of limin of fn x dx. This is n going to infinity is less than equal to limin of integral fn x dx n going to infinity. And the second result is that section of a compact set K in X cross Y is compact. So a section is defined as, so K is, let's say K of X equals to Y such that x, y is in K. So this is called a section. So we'll need these two results in order to prove our main theorem, which is we want to show the existence of mu star and v star under these assumptions, under these three assumptions. So what did we do in the finite state setting to prove the existence of v star? So we set up a Bellman operator, and then we showed that the Bellman operator converges as k goes to infinity. We iteratively apply the Bellman operator and it converges to a fixed point of the Bellman operator, which is the optimal solution. The argument here is somewhat similar, except that we are not making the contraction argument in this particular case. Instead, we are doing it via some other argument, which is sort of creating a strictly increasing function. Creating an increasing sequence of function and showing that that particular function has a limit. So let me define the Bellman operator in this case. TVS in A of S CSA plus expected value alpha times expected value of FSA W. So this is the random variable here. With respect to which this expectation is being taken. And the value iteration algorithm here is going to be my V0 is identically 0 and Vk plus 1 equals to TVk. That's my value iteration algorithm here. Any questions so far? So the Bellman operator is defined exactly the same as is the case in the context of the finite state, finite action setting, except that we didn't have to worry about the infimum. We had the minimum because you are in a finite action setting. So if you have a finite set and you have a function which is all finite at every point, then of course the infimum will always exist, and so you don't have to worry about minimum. But right now, because we don't know if a minimum exists or not, we have to work with infimum until we are able to prove that infimum exists, and therefore we can replace it with minimum. Any question? What would you do if you were in this particular setting? What do we already know? So we know that C is an inf compact function. So in particular, it's lower semi-continuous because its sub-level sets are closed. The other result was we can always restrict our attention to one of the sub-level sets because it's compact. The infimum will always exist, but that's for C. Now I have this additional term here, expected value at the future state. So what should we do? What should be our step? So this is lower semi-continuous and inf compact. I need to show that this is lower semi-continuous. Okay, so that's the first step. So step 1. How should I show that this expected value of the future value is lower semi-continuous? So I'm going to pick SN graph of A such that Sn converges to S, An converges to A. So I have lim in n goes to infinity integral Oh, one important thing. So remember that cost is non-negative, right? So at every point of time, my value functions will be non-negative because I'm not subtracting anything. In this expression, I'm starting from 0 and I'll continue to add the cost at every point of time. So this Vk is always going to be non-negative. So I'm picking a value function V which is non-negative, and I'm going to pick V that is LSC. Okay, so I picked the V which is non-negative and LSC. This is a distribution density function. So this is always non-negative. So I have non-negative function multiplied by non-negative function. So this whole function is non-negative. So I have limit of integral of f and dx, limit of integral of positive function dw. And this function is of course a function of Sn and An. So therefore, it's you can call it a function of n. Now this by Fatou's lemma is greater than equal to integral limit of v f Sn An w nw dw. I've just applied Fatou's lemma here. So f is continuous function here because we required the transition function to be weakly continuous. So this is continuous. This is lower semi-continuous. What is limit of lower? So this one converges to f of s a w in the limit. V is lower semi-continuous. So I have something that converges. Let me call this xn. Well, it's actually Sn prime. It's the next state for given Sn An pair. It's the next state. So remember we said that limit of, so if V is LSC, then limit of V must be greater than equal to the value at the limiting point. So this is greater than equal to integral V f s a w n w dw. So this is by property of V being LSC. So this is Fatou's lemma. And this is V is LSC. So we covered one of the properties of lower semi-continuous function, that in the limit it takes a lower value. So in the limit it is taking a lower value and I'm just multiplying it by the usual expected value. Okay, any question? So this implies that expected value of V f s a w is LSC on SA. It's lower semi-continuous function on, let me write it as graph of A. V is LSC and F is continuous. Everyone understands this argument? So I pick a sequence, the sequence converges to S and A. I look at the expected value of the value function at the future time step given S and An, and it turns out I can push the limits inside with a greater than equal to sign because I'm applying Fatou's lemma, and then I know that because value function is lower semi-continuous and F is continuous, this particular inequality holds because the value function will always take the lower value at every limiting point, and that's proves that the expected value of V at the future state is lower semi-continuous on graph of A. Okay. So I start with value function 0. Is 0 LSC? Is 0 lower semi-continuous? So it's actually continuous function. It's identically 0. So it's a continuous function. So at time t equals to 0, this is definitely true, and F is continuous, and that's by assumption. That's the assumption we made in the previous lecture, that its transition kernel is weakly continuous. Okay. Now step 2. I'm going to call this function j of SA, although j is something that we've already used. We call it j bar of SA, which is C SA plus alpha again. V is non-negative. V is greater than equal to 0. V is LSC. My claim is that this function j bar is also inf compact. So C is inf compact. This is a lower semi-continuous function, non-negative lower semi-continuous function. I'm adding a lower semi-continuous function to an inf compact function. I'm going to get an inf compact function. How should I prove that? So I have to look at the sub-level sets of this particular function j bar, and I have to prove that it is compact. So let's look at the sub-level set. Let me call this B of lambda. This is SA such that j bar of SA is less than lambda. I'm going to make a claim that this is a subset of SA. CSA is less than equal to lambda. Let's think about it. So my V is non-negative, right? My V is non-negative. I'm doing expected value of a non-negative function. So this term is non-negative. Alpha is between 0 and 1. So this whole term is non-negative. Now if I pick a point SA in this particular set, I have CSA getting added with a non-negative value. Okay, and that's less than equal to lambda. Obviously, C of SA has to be less than equal to lambda, right? So therefore, this particular set is a subset of this set, and I know that this particular set is compact by assumption. That's the assumption here. C is inf compact. So sublevel sets are supposed to be compact. What about this set? This is a lower semi-continuous function. This is a lower semi-continuous function. Alpha is a positive number between 0 and 1. So this is a lower semi-continuous function. I'm looking at the sub-level sets of lower semi-continuous function. It's closed. This set is closed. I have a closed set within a compact set. What did I say compact set means? It's closed and bounded, infinite dimensional. So it is closed and bounded set. I have a closed set which is a subset of a closed and bounded set. So this must be closed and bounded as well. So therefore, Bj lambda is compact. Okay, so step 2 is complete. Step 3. Recall that my T V of S is in A of S, J bar of SA. My assumption is V is greater than equal to 0. V is LSC. I want to remove this infimum. I'm very worried about this infimum. I want to remove it. What's the way to remove the infimum? I want to make it minimum. How do I make it a minimum? Sorry? Should we check?
This stress is zeroing for the closed function, so it can be proved that it is attainable.
Right.
So we can treat the increment to the minimum.
Correct. So how do I prove that the infimum can be replaced with minimum? What do you suggest? What should I do? So what have we proved so far? We have proved that J bar is LSC. So we have proved J bar is LSC and in compact. So step 1 proved that it is LSC. Step 2 proved that it is inf compact. Right? Any idea? Any thoughts?
That's like the Weierstrass theorem.
Which?
Weierstrass theorem.
Weierstrass theorem, yes, I understand, but Weierstrass theorem requires that the action set be compact. But I don't really have a compact set here.
Oh, yeah.
I have an inf compact function being minimized over a potentially infinite set. So I cannot directly apply Weierstrass theorem, but I want to apply Weierstrass theorem because that's what allows me to replace infimum with minimum. So what should I do?
So another way is to prove that J bar is in compact.
But we have already proved that it's inf compact, right? That's what I have proved here.
And the set is and the constraint set is closed or not?
A of S is not closed. We haven't made any assumption on A of S. A of S could go all the way to infinity. Okay. So here is the trick. For every state S, I'm going to pick a random action in A of S. So pick A in A of S and look at the set J bar of SA, S Okay, maybe I'll pick A tilde. J bar of S A tilde. So what I've done is I've created a sublevel set. Is A star going to lie in this sublevel set? It's going to lie, right? Because this is a random action. I've picked some random action at which this cost is finite. So this is some random action that I've picked. I know that my optimal action must lie within this set because I have to minimize, right? So I have to infimize here. What about this set? So I know that S of A, S comma A of this particular set is compact. What I'm doing is I'm looking at a section of this particular set. So what is a section? So I fix one of the variable to be X and I'm varying the other variable and I'm looking at the section. What happens is you have a closed and bounded set. You look at a section, the section is also closed and bounded. Okay. So this set is compact. So this, let me denote this by D S A tilde. So I'm denoting it by dj of S A tilde. This is a compact set. And then I can just say that T Vs is minimum over A in okay. So now I've replaced the potentially infinite set to a compact set. I can replace the infimum with a minimum because of the extreme value theorem. So this is a trick commonly used in optimization. You have like a potentially infinite set. You pick some random point and then you look at the sublevel set. Sublevel sets are compact. So therefore, you can just restrict your attention to the sublevel set and you get a optimal solution. Now there's another thing that happens at this particular point, which we will not get into, but there's a whole theory of mathematics called measurable selection theorem, which says that the argmin here is actually going to be a measurable function, which means that it is well defined continuous and or discontinuous function. So that gets applied and then it basically shows that TV is also a measurable function, and in particular TV is a lower semi-continuous function. So let's talk about TV being lower semi-continuous. I think that's step 4 and I don't have space. I want to look at this particular set. TV is less than equal to lambda. Can I prove that this is a compact set? So what is this particular set? This is equal to S such that J bar of S A star at S is less than equal to lambda, which is a subset Let me use A tilde again here. So I know that this is also a section of a compact set, and so this is a compact set, and this one is a closed set. Wait. So this is a compact set. I think this one is a closed set. Let me check the proof once. Oh, right. It's a section of a compact set. So this one is a section of a compact set. So here I was considering the section of at a specific S. Here I'm considering the section at A star of S, which is the optimal, the argument point here. So that's the point A star of S here. So I'm looking at the section of a compact set. So therefore this one is also a compact set. Therefore this is a compact set. So TV is inf compact. So I'm going to pause here for a bit. Let you digest the proof, step 1 to step 4, and then we'll complete the rest of the proof. Any questions so far? Yes. Yes, please.
So what does the GRA mean?
Oh, we introduced this in the previous lecture. GRA is S comma A, S is in S, A is in A of S. So all the feasible points in the state cross action space. Okay, any question so far? Okay, so what did we do? We proved that if I start with a non-negative V and lower semi-continuous V, my expected value of future value is lower semi-continuous. That allowed us to prove that J bar defined in this fashion, sum of the cost, current cost and the future value with a discount factor, that's an inf compact. That allowed us to remove this infimum with minimum, and that's extreme value theorem, and then you can show that for every S you can define it in this particular way, and the resulting TV that we get is a measurable function that uses measurable selection theorem, which we didn't talk about. And then that allowed us to show that TV is also an inf compact function. And inf compact functions specifically are lower semi-continuous, something that we talked about again in the previous lecture. So TV is lower semi-continuous. I have added a positive cost function and a positive value, and I'm doing the minimum. TV is non-negative. So I started with a non-negative and lower semi-continuous cost function. I get a non-negative and lower semi-continuous cost function after the Bellman operator is applied. Now, I started with a non-negative and lower semi-continuous value function. I applied this operator, Bellman operator, again and again. At every point of time, I get a non-negative and lower semi-continuous value function. In particular, Vk plus 1 is all inf compact. These are all inf compact functions. Consequently, in the limit, what we get is an inf compact function. Okay, so we get this particular function will I'm going to erase this side. So I have V0 less than equal to V1 less than equal to V2. Vk is in compact. So you have an increasing sequence of functions. I can define my V star of S to be limit k goes to infinity Vk of S. Why does Vk of S exist? By monotone convergence theorem. So if you have a sequence of increasing values, it converges to a limit. I'm going to define that limit as V star of S. The sublevel sets of V star of S is intersection sublevel sets of each of the value function. That's because it's increasing. This value function is increasing. So at V star of S, we can look at the sublevel sets of this particular function is going to be sublevel sets of each of these intersection of the sublevel sets of each of these functions, and this is compact. So we are taking an infinite intersection of compact sets. I get a compact set. So V star S is inf compact. Okay, so this is roughly how general state MDPs are treated in the literature. Yes.
So how do we prove that V0 is increased, monotone increase?
Because cost is positive. Remember, cost is 0 to infinity. Right? So my cost is positive. I started with a 0 function, so at every point of time I'm minimizing a positive function. So I get a positive number. Okay.
I have a question.
Yes, please.
I need some point. We assume that V is bounded, so we can.
We don't assume that V is bounded.
So why the V star?
But at every state, you will get a bounded cost.
Yeah, so we know that V is monotone and why V star exists, why the limit exists.
No, so remember that. So monotone things will always have a limit. Now you can argue that the limit could be infinity.
This needs bounded.
No, you need bounded for each of the, at every state you want VKS to be bounded, but you don't want VK to be uniformly bounded.
Oh yeah.
Right? So like for instance, S transpose QKS, let's say this is your function and QK is a sequence of positive definite matrices converging to a limiting positive definite matrices, as is the case in LQR problems. I don't know if you've studied LQR, but if you have a sequence of QKs that converges to a limiting QK, and so at every S, the value function is increasing and it's bounded, right? But you don't want the entire value function to be bounded. Okay. Any other question? Okay, so things that I have brushed aside in this entire proof is the measurable selection part right here. And naturally, if you go back to Feinberg and Lewis paper from 2007, which is what this particular proof is based on, you have fairly general state space, fairly general action space there, and your transition kernel is weakly continuous. So you don't need to have a specific function f for that particular proof to work. So it's fairly general, but we are considering a very special case here because the proof is much easier to do in the class. Any questions so far? No? Okay. So if you go back to the history, from 1960s onwards, people have been studying problems of this type, and these are not the only assumptions under which the existence of mu star and By the way, V star is inf compact, so then I can get mu star as argmin A in AS, C SA plus alpha expected value of V star. Okay, so I can get mu star from doing the argmin of the future cost with respect to V star, and this is the optimal policy, and this is the optimal value function, for the MDP. So now the cool thing that I wanted to mention is there are many assumptions here. So I've made a specific set of assumptions, and I've showed you that you have an existence of V star and you have an existence of mu star. But there are papers with completely different assumptions and books with completely different set of assumptions, completely different proof, proving the same result. So don't think that this is the ultimate proof. Depending on the situation, you might need a different proof for proving the same result. The reason why I particularly love this result, as I mentioned, even if I have a deterministic system, so I don't have any noise, this proof still works because it requires just a continuous state transition function. Okay. So for robotics application, so one of the things, if I go back to 2010 onwards, when I was a graduate student, I was very surprised that the proofs for MDPs are written for strongly continuous transition kernels, but everyone is applying reinforcement learning on OpenAI gym environment, which are all deterministic transitions, and still the results are pretty good. Okay, and I was always confused why the results good when the proofs require strongly continuous transition kernels, and the reason is it works for weakly continuous transition kernels as well. Okay, so next topic is I want to add more assumptions to this, and I want to show that V star is a Lipschitz continuous function. Okay, why is Lipschitz continuous function important? Why is it important? Sorry? No, not it. That's sorry.
You can implement them.
You can implement them. So neural networks are very good Lipschitz function approximators. Okay. So another thing that puzzled me throughout 2010 to 2020 was the theory. By the way, this whole proof is saying that V star is a measurable function. It's a lower semi-continuous function, so it can have discontinuities. I know you have done this fitting discontinuous function using neural network in assignment 1. That was your assignment 1. What did you find? What did everyone find in the class? If you have a discontinuous function and you have a neural network, very difficult to fit a neural network with a discontinuous function. So now the theory says V star is potentially discontinuous, yet people who are using deep reinforcement learning are able to get very good results with robotics, with chess playing, with this and that. What does that mean? There must be some Lipschitz continuity properties of the true value function. That's why the deep neural network is able to approximate that value function, and we are able to get such good performance from chess playing reinforcement learning algorithms and Go playing reinforcement learning algorithms and so on and so forth. Okay, so that's why the second result is important. I want to prove that V star is Lipschitz continuous. The setting is going to remain the same. So this part is going to remain the same. I really love zero function. Zero function is Lipschitz continuous. Zero function is the smallest function, smallest non-negative function, and so on and so forth. Okay. Time for more assumptions. Okay, I am going to introduce a metric called Hausdorff metric. So I have two sets, A1 and A2. These are subsets of A. So it looks like this. This is my A1. This is my A2. I want to find the distance between these two sets. Everything inside, by the way, is included. So A2, everything inside is included. A1, everything inside this bounding box is, or bounding curve is included. What do you think is a reasonable metric or a reasonable distance between these two sets? So something where if these two sets coincide with each other, then the distance should be 0. If they are apart from each other, the distance should be positive. So how would you define the distance? I've drawn two sets here. So think about it for a minute while I erase the board. What do you think is a good distance between the two sets? Any idea?
Projection.
Not quite projection, because projection requires you to be in a Hilbert space setting. We are in a metric space setting. So, yeah. Yes.
The intersection over U. That's a popular metric for water.
Yeah, but intersection, what did you say?
Intersection over U. Like, I guess you have to be able to measure the size of the set.
Measure the size of the set. So I think that's roughly what the Hausdorff metric is trying to do. So we look at all the points in A2 that's not in A1, and look at the furthermost point from A1. So that's this point, and maybe this is the distance between the set A1 and the furthermost point in A2, which is not in A1. And I'll do the same thing. I'll pick, so this is A2. I'm going to look at the furthermost point in A1 and look at the distance between this, and I'll take the max of these two distances. Okay? And that's called the Hausdorff metric. So it's defined as, I'm going to define it by dH of A1, A2 equals to max sup A in A1 in A1 in A1, A2 in A2, dA A1 A2 sup A2 in A2 in A1 in A1 dA A1 A2. Okay, so I'm just ordering the sup and inf. I'm doing it over two different sets, and I'm taking the max over these two sets. So this is this distance is this one, and this distance is this one. Yes, you have a question?
So the distance,
Mm-hmm.
so it can be, for example, consider the Hilbert space. Okay.
Yeah.
It can be a L2 norm, right? L2 norm.
It can be L2 norm.
Yeah.
This could be L2 norm.
And you can be infinite norm, or it's.
That's right. It can be infinite norm.
We have freedom here to reach that.
Yes, you have the freedom to pick whatever metric you want to pick on the action set. Okay, anything you want.
And this invert BA looks a little bit like projection.
So it depends on what you mean by projection.
That means in norm, the norm.
You need a Hilbert space for projection.
Yeah, so the thing is, in Hilbert space, projection becomes much easier. In general spaces, generally you don't call it a projection, but you can think of it as projection. Yeah. There are attractive properties of projection in Hilbert space, but if you go outside of Hilbert space, you lose all that property. Okay. Any other question? Okay. So now I want to prove that this V is Lipschitz at every point of time. So certainly I need to prove, I need to assume that the cost function is Lipschitz and this F is Lipschitz, and I need to assume something about the Hausdorff metric between two sets. So assumption, let me add one, C is Lipschitz. And LC is the Lipschitz coefficient. F W is Lipschitz. All of you are aware of Lipschitz function? Anybody who doesn't know what the definition of Lipschitz function is? Everybody knows? Okay. So FW is Lipschitz with respect to LF W bar. And I'm going to define LF as integral and the third one is DH AS1 AS2 is less than equal to LH DS S1 S2. By the way, these assumptions are in addition to these assumptions. Okay, so you cannot replace these assumptions with this assumption. You need to assume this, so the value iteration works. Then you have to assume this, so that the value functions are Lipschitz continuous. Any questions so far? So remember, I have like 3 terms here. This is a function of S and A. This is a function of S and A. This is a function of S. So I have to make the assumption of Lipschitz continuity with respect to each of these assumptions, each of these values. And then I'm going to make an additional 4th assumption that LF alpha times LF times 1 plus LH is less than 1. So alpha is the discount factor, LF is this number here for the transition kernel, and then LH is how the sets are changing as you change the state space S, as you change the state S. So if your LF is very high, you want your LH to be as low as possible. So you don't want, so if your Lipschitz coefficient of the function f, that state transition function f, is very high, you want your LH to be as close to 0 as possible, which means that the set of actions doesn't really depend on state that much. On the other hand, if your LF is small, then your LH could be somewhat high. And if both of these are high, you want to make sure that your alpha is as small as possible. Now, if you're using, let's say, deep reinforcement learning with a shallow neural network, so a deep neural network can approximate very high Lipschitz coefficient functions. but a shallow network can only approximate low Lipschitz coefficient function. So in that case, if you are not able to approximate the Lipschitz coefficient of V star, you will get pretty bad results when you are running deep reinforcement learning. Okay, I know we haven't talked about deep reinforcement learning, but I'm assuming that because you guys are enrolled in this class, you must have seen at least a few examples or papers or whatever of deep RL. Okay, so let's go about proving this result. Yes.
I just ask you, what does you write a bar over L?
So this is a function of W, right? So I've removed S and A. So this is a function of W that has the Lipschitz coefficient of this. Now I'm averaging the Lipschitz coefficient with respect to the distribution of W in order to get LF.
So the bar over LF, the bar over LF means averaging.
This is the averaging. This one is just at every W. This is what the Lipschitz coefficient looks like. This is just a notation. This is not averaging.
Okay.
Yeah. So I want to have the notation where I have LC, LF, and LH. Just 3L. I don't want to put bar and stuff there. Okay. Okay. So one thing that you can convince yourself, I have a Lipschitz continuous function. I have a Lipschitz continuous function. I have a Lipschitz continuous function. I'm taking the expectation of this Lipschitz continuous function. So sum of Lipschitz function plus Lipschitz function is a Lipschitz function. Okay. So all I have to do is prove that infimum of a Lipschitz function over a Lipschitz set is Lipschitz function. So that's all I have to prove. So I start with a Lipschitz value function. At every point of time, I want to prove that this infimum operation is going to get me Lipschitz. By the way, I can remove the infimum now with minimum because I have proved that the minimum exists using 1, 2, 3. Okay, so I'm going to prove this result. So I have, let me call this J bar as I had used in the previous proof. So I have minimum of, so pick S and S tilde. I'm going to look at TVS minus TVS tilde. Right? So I want to prove that if V is Lipschitz, then this particular thing is Lipschitz. This is minimum A in AS, J bar SA minus minimum A tilde in A S tilde. Sounds good? So lots of max. Sounds reasonable? So this is an independent function, this is an independent function. I can push the maximum outside. So this function doesn't depend on A tilde at all, only this one. Max of negative is negative of min. Okay. What should I do now? I know that this one is a Lipschitz continuous function. What's the Lipschitz coefficient of J bar? So this is less than equal to this max min of J bar SA minus J bar S tilde A tilde. max of A tilde in A Can someone tell me what the Lipschitz coefficient of this is? J bar and J bar of SA minus J bar of S tilde A tilde.
LC plus L five
LC plus
LR times LV. Yeah.
right times DH DS S tilde plus DA A tilde. So I took a function, I looked at the upper bound, so that this is the upper bound of this particular function. I have max over A tilde, min over A of something that's a function of S and S tilde, so that part doesn't participate in this max min operation. This one does. What does this look like? What does this term look like? dA of A tilde with a max min. Max min dA of A1 A2. Okay. So this is actually less than equal to LC plus alpha LV LF ds S tilde plus LC plus alpha LV LF, and I'm going to replace the max min by dH of A S tilde, and I have made the assumption that dH is less than equal to LH times the ds. Okay, so I made the assumption 3, so I can substitute this as the same thing LH ds S tilde. Right, so I have everything in terms of ds S tilde. So I have some constant here multiplied by LH times ds S tilde, the distance between S and S tilde. So what do I have here? So it seems to me that I have some sort of recursion going on, wherein, by the way, I can switch the order and I get the same result. Okay, because nowhere I have used the fact that I'm doing S here and S tilde here. So I can switch the order, get the same upper bound. So therefore, this is the Lipschitz coefficient of TV. Any questions on this? I have to erase this. So I just want to make sure that all of you agree with this part. Any questions so far? No? Okay. So let me erase this. Let me write it here. This is less than equal to LC plus alpha LV LF 1 plus LH ds S tilde. So I can write it as LC1 plus LH plus alpha LV LF1 plus LH. TS S tilde. Okay, so now I have a recursion again. So this is the Bellman operator applied to V. I have the Lipschitz coefficient of V right here. So I have Lipschitz coefficient is equal to alpha Lipschitz of V LF1 plus LH plus LC1 plus LH. So Lipschitz coefficient of TV is Lipschitz coefficient of V multiplied by some term which is by assumption less than 1 plus some constant which doesn't depend on Lipschitz coefficient of V at all. What does this converge to? What does this recursion converge to? So I started with a zero function. At every point of time, I get a Lipschitz continuous function. So this, remember that Vk converges to V star. So Lipschitz of V star equals to LC 1 plus LH over 1 minus alpha LF 1 plus LH, which is less than infinity. This result is proved in Hinderer 2005. I think the title of the paper is something to do with Lipschitz continuity of value function in Markov decision processes or something like that. So even though most of the people, not many people know about this result, I think that most of the cases where deep reinforcement learning works or neural network based reinforcement learning works is the case where V star is Lipschitz continuous. And if you have non-Lipschitz continuous value functions, deep reinforcement learning will give you a lot of errors, especially where the value functions are supposed to be discontinuous. Okay. Any questions so far? Any questions so far? No? All good? Okay. So if you assume 1, 2, 3, 4, 5, 6, 7, you get a Lipschitz coefficient value function. Now let's look at monotone MDP. I have about 10 more minutes. So hopefully I should be able to cover monotone MDP. So let's talk about some problems in business. How many of you follow the interest rates at the federal government level? Interest rates that the, no one? Okay. All right. I was planning to make a argument that whenever unemployment is high, the interest rate should go low. Whenever the unemployment is low, the interest rate should go high. What does that tell you about the policy? There seems to be some monotone structure in the policy. So if something is going low, something else has to go high, something is going high, something else has to go low, right? So that's studied under the umbrella of monotone MDP. So that's what I want to talk about. We are only going to look at the monotonicity of the value function, not of the policy, right? But there are, okay, so there are very few papers that talks about monotonicity of the policy, but I think it can be proven. And but nobody has written a paper on it. So hopefully you can write a paper on it. So what is the setting? Remember, my state space is Rn cross n cross z. So on this space, there is a natural ordering wherein we say that S is less than equal to S tilde if and only if Si is less than equal to S tilde I for all I. So I have this vector S, and each element of the vector is less than equal to the elements corresponding element of the vector S tilde. That's the ordering. That's called a partial order. That's called a partial order on the state space. Now I'm going to make some assumptions, as always. So S is less than equal to, I wish I could find a better chalk. S is less than equal to, sorry, S tilde. I'm going to assume that A of S tilde is a subset of A of S. C of SA is less than equal to C of S tilde A for all A in A S tilde. And the third requirement is Fs AW is less than equal to So example I want to keep in mind is St plus 1 equals to St plus At minus Wt. Or I could even do the following: max of St plus At minus Wt 0. This is element wise maximum. So you have a vector. Okay, so I'll give you an example. I will wait for everyone to note down and then I'll give you the example in this setting. Okay, so this is the example I have. This is a MDP for Kroger, and Kroger has ST amount of items in the inventory. So they have n items, and ST denotes the number of items in the inventory. AT is the amount of inventory they are ordering today, and so it will come by evening today. And WT is the amount of people buying that inventory. Okay, so you have 5 gallons of milk and 10 pounds of pasta. They've ordered some amount of item, and then 2 gallons of milk were sold and 5 pounds of pasta was sold. So that's minus WT. Inventory always has to be non-negative. So then I have to do this max over 0 condition. So if there is someone who came in to buy pasta, but the pasta was over, so then the inventory is not going to go down by 1. Okay. So in this case, you can notice that the state transition function is actually monotone in S tilde. So if I pick a higher inventory level at the start of the day for the same amount of order and the same amount of customers who come in, my ST plus 1 will be higher, right? So that's what this assumption means. And the cost with higher inventory has to be higher, and the number of items you can order with higher inventory must be smaller than the number of items you can order with lower inventory. Okay. What I want to prove, the theorem is that V of S is less than V of S tilde. So V is monotone. This is known as that the value function is monotone increasing. The idea is again the same. We'll prove it by induction. I start with a value function that is obviously monotone increasing, I mean non-decreasing in this case. So V0 is equal to 0. My cost function is monotone. My value function is monotone. My state transition function is monotone. And this one is not quite monotone, it's sort of reverse monotone. So remember A of S tilde. So S tilde is the higher state, and A of S tilde is a subset of A of S. Okay, so how do we prove this? This is expected value of V of F S A W let me put V star here. So this is so V is monotone. So assume expected value of V of F S A W is less than equal to expected value of V of F S tilde AW. So for every AW, you know that this particular term is higher, so V of this term would be higher, and so the integration, the expectation with respect to W will also be higher. So that part is easy because V is monotone. And then I have minimum of A in AS J bar SA is less than equal to minimum of A in AS tilde J bar in okay. So this one implies that my J bar of SA is less than equal to J bar of S tilde A. That's because my cost is monotone. My cost has the monotone structure, and my value function also has the monotone structure. So I combine the two, I get this result. So that gets me to this particular inequality. J bar of SA is less than equal to J bar of S tilde A. So I'm minimizing over the same set here. Now how do I get this inequality? This set is bigger, this set is smaller by assumption. Okay. So I have a function, I'm minimizing over a bigger set, I'll get a lower value. I'm minimizing it over a smaller set, I'll get a higher value. So that's why I get this inequality. So this implies TV is monotone. So I start with a monotone function, I keep getting monotone functions. In the limit, I get a monotone function. Okay, that's the argument. My PhD student proved this result in a paper in 2022. So that's where this proof comes from. It's not that this proof was not known earlier. I think for Different setting, it was known in some economics literature back in 1989, roughly. But what we came up with was a simpler proof than what they did in their book. So monotone structure is extremely important in business setting, finance setting, inventory optimization setting, logistics setting, because there is a natural order in many of the things that you are trying to optimize. So if you have higher inventory level, you have to pay a higher cost. Okay, so some of this assumption is automatically satisfied. So if you go to a shipping company and you are trying to optimize the cost for a shipping company, most likely you will be dealing with a monotone MDP. Okay, or if you go to Kroger is headquartered in Cleveland. Okay, so that's all I have. I was able to complete all the 3 results. My office hours is right after this class, so if any of you have questions on the stuff that we discussed, please feel free to reach out to me in office hours. Okay, thank you.